Hello friends, so welcome to the second lecture of electric potential energy. So in today lecture we will discuss about the electric potential. Already we have discussed about electric potential energy. Then what is the need to study about the electric potential? So electric potential is characteristic property of the point in the electric field region. So it is characteristic property of a point in electric field region in electric field region. Now question arises how it is a characteristic property. For example, there is a charge q and its effect in its surrounding. So let in its surrounding point p is there. Now if you are bringing any charge q1, so here the electric potential energy at that point p will be written as u1 for q1 charge. Similarly, if you are bringing a charge q2 here, so for that, the electric potential energy will be written at that same point is U2. So here, for the same point, U1 and U2 are different for different charges because you are doing different work to bring this charge against the field of capital Q charge. But at point P, if we want to define something that is not changing with the change of the charge, so for that we define the electric potential. So electric potential is defined as what? It is the amount of work done to bring unit positive charge to this point P in a given electric field region. So for example, if I will write this U1 and I define the electric potential of this point is Vp, then U1 can I write Q1 Vp. Similarly, if I will write U2, then it is what? Q2 Vp. Q2 Vp. So you can see here U1, U2 are different, but Vp for both are same. So here we can define electric potential as what? We can define electric potential as a the potential energy divided by charge. And its unit will be joule per coulomb. Correct? Okay. 1 volt equals to 1 joule per coulomb. Its SI unit is volt. SI unit is volt. SI unit is volt. It can be also defined as it is the amount of work done. It is the amount of work done to bring unit positive charge from infinite to given point P in electric field region to point P to point in electric field region. Electric field region. So this is what electric potential. So why we are defining electric potential? Even we know electric potential energy because in this way we can define the characteristic property of that particular point that is not changing with different charges. Correct? Okay. Now electric potential due to the point charge in its surrounding. So let us consider one point charge Q here. Now in its surrounding at any point P, I will take another charge Q naught. Correct. So what is the interaction energy between these two? Interaction energy already we studied in last class. Interaction energy is nothing but the potential energy. So potential energy is K, Q, Q naught. And the distance between them is R. So it will be written as divided by R. So electric potential at point P defined as U by Q naught as we discussed now. K, Q, Q naught by R divided by Q naught. So it will be K Q by R. Correct? Okay. So this is what electric potential to the point charge in its surrounding. Now, if there is an extended charged body, then how to find the electric potential? So electric potential due to charge extended body. So if a body is not point, it is the extended body. and it is charged. It is charged. So we cannot directly find, already we know that Coulomb's law is only applicable for point charge. Same way we cannot find electric potential also for extended body. Correct. Okay. So as we cannot find the electric potential for extended body directly, so what I will do? I will take a elemental charge here. Let total charge is Q. Q is total charge. Total charge. Correct. So elemental charge is dq, and let a point P is here. That is what r distance from here. So due to this elemental charge, first I will find the electric potential at point P. So here I will find dV, a small electric potential due to this small charge. It is what? K dq by what is the distance? R. Now to find the total, due to total charge electric potential here, we will integrate it. V equals to integration of dV, that is nothing but integration of K dq by R. With a few examples, we will understand how to integrate, how to take potential, how to find the potential due to different extended charged bodies. So here, first one example is electric potential due to uniformly charged rod at its axial point. So just we consider a uniformly charged rod. Uniformly charged rod. Now due to this uniformly charged rod, I will find the electric potential at point P. Let this is at r distance from here and the rod having the length L. Rod having the length L. Now here total charge is Q. This is what? Total charge. For any extended bodies, we are defining linear charge density, areal charge density, cubical charge density. Here, because it is a rod, so that's why we define linear charge density, lambda, denoted by lambda. Linear charge density. Correct. It is defined total charge divided by length, Q divided by L. Correct. Okay. Q is what? Total charge. Q is your total charge. Now, how to find electric potential at point P? So for that, I will take the elemental charge here, elemental charge here. So here, elemental charge, how to take? Let this elemental charge is at x distance from here. Correct. So this elemental charge is what? dq. Correct now. Now, here, dq is a charge on dx length. Dx length. So it can be also written as dq is total charge per unit length is q by L, and dx length means it will be multiplied by dx. That is the dq. It can be also written as lambda dx. Correct. So now it is dq charge. As we have discussed already, if we have to find due to extended body electric potential, we will first take elemental charge on that, and then we'll find electric potential due to that elemental charge, and then we will integrate. Same thing we are doing here also. So here electric potential will be dV equals to K dq by what distance it is from here? X. It can be also written as K lambda dx by x. Now next step what we have studied, we'll integrate it. So we will integrate it. So to find the total potential, K lambda integration of dx by x. Now here x is changing from where to where? This rod started from this point P r distance and ending at r plus L, because rod length is what? L. This is rod length L. Correct? So r to r plus L. Now we will integrate this. So here K lambda integration of dx by x, you should remember. Integration of dx by x is ln x. Correct? So you'll use this formula here. So it will be ln x. Limits are what? R to R plus L. So K lambda, we'll put this limit here. Ln, first upper limit, R plus L minus lower limit, ln R. So ln A minus B is ln A minus ln B is ln A by B. Correct? So here we will write K lambda ln R plus L by R. Correct. This is the electric potential at point P due to the rod, due to uniformly charged rod. Here we find it at axial point. At axial point. This one at axial point we find it. Correct now. Now next, if we have to find at equatorial point, what is the meaning of equatorial point? If I will take a rod, uniformly charged rod, same way, its linear charge density is Q, sorry, lambda, total charge is Q, lambda is Q by L, where L is the length of the rod, and Q is the total charge, total charge, correct now. So we have to find at equatorial point. So let equatorial point is P. What is the meaning of equatorial point? If we will draw the perpendicular on this rod, it will equally divide this rod in two equal halves. Now due to this rod, if I have to find the electric potential, how will I find? So let this point P is R distance from the center of the rod. Now at X distance from the center on the rod, dx length I will take, dx length, elemental length. On dx length, the charge is dq, small charge. And this is x, this is a what? It is a right angle triangle. So r and x, this distance will be root under r square plus x square. Now due to this dq charge, I will find the electric potential at point P. And you know that electric potential is a scalar quantity. So no need to think about direction. Directly we can write dv equals to, what is the charge? K dq divided by distances root under r square plus x square. Now here variable is x. X is changing. Reference point is center of the rod. Right side is positive, left side will be negative. So it is in center. That's why it's minus L by 2 to plus L by 2. Limit is minus L by 2 to plus L by 2. So to find total potential, we will integrate it dv. So it will be K dq is lambda dx divided by root under r square plus x square. Correct? And limit when we will do, it is minus L by 2 to plus L by 2. But the question arises how to integrate this. So whenever we have to integrate this type of term, correct, we have to use what? Integration by substitution method. You can see here one triangle is forming. So we can relate an x and r by using this angle theta. So in the triangle, tan theta equals to x by r. So what is the x? R tan theta. Correct? So here x equals to r tan theta. Correct. So we will differentiate with respect to theta both sides. So it will be r secant square theta. Correct. So dx is what? R secant square theta d theta. Now we'll substitute this value in this integral so that we can integrate it. We can bring in the integration form. That's why it is known to be as a substitution, integration by substitution method. So here k lambda we will keep outside, v at p. K lambda is outside. Integration of what? Integration of dx value will put r secant square theta d theta divided by here root under r square, and x value is r tan theta. So we'll write r square tan square theta. Correct? So here it will be k lambda integration r secant square theta d theta. Now divided by r square will take common, outside r will come. 1 plus tan square theta, it will become secant square theta. Outside will come, it will be secant theta. Correct. Now secant theta, 1 cancel out, r cancel out. So it will be, and limits as I told you, minus L by 2 to plus L by 2. Here also same thing. So k lambda integration of what? K lambda integration of secant theta d theta. Integration of secant theta d theta. Secant theta d theta. Correct. Now here k lambda limits are minus L by 2 to plus L by 2. And here secant theta d theta. We cannot put the L by 2 in the theta. Why? Because this is the limit of x. X is changing from minus L by 2 to plus L by 2. So again, we have to convert secant theta into x form. How will we convert? As we know the triangle here. So secant theta, how can I write here? What is the secant theta here? So first we cannot directly put secant theta. Again, the integration form it will come. So first we will integrate secant theta. So secant theta integration is integration of secant theta d theta. Then it will be ln secant theta plus tan theta. Correct? This formula you should remember. Now we'll put this value k lambda ln mod secant theta plus tan theta. Correct? Now you will put the secant theta and tan theta value here. Secant theta you will write secant theta from this triangle you can see h by b. So root under r square plus x square by r. Root under here you will write k lambda ln mod root under r square plus x square by r. Then tan theta p by b. Opposites by adjacent p by b. So that is what x by r. X by r. Correct? And then you put the limit minus L by 2 and plus L by 2. Correct? So now you will write it is k lambda ln mod here x value you put L by 2, so it will be root under here it will be r square plus L square by 4 and divided by r plus here minus L by 2r or we'll write minus L by 2r. Correct? Minus L by 2r. Okay. So this is the final potential at point P due to what? Due to the uniformly charged rod at equatorial point. Correct? Understood? So next we will discuss one more case, electric potential due to uniformly charged ring. So first case 1, at the center of the ring, at the center of a ring, at the center of a ring, sorry, at the center of a ring. Here I will take uniformly charged ring, and let the radius of the ring is r. So I have to find the electric potential at the center of the ring. So I will take what? I will take a dq charge, as I discussed with you already. We have to take first elemental charge dq. Total charge is q. Total charge. So due to this dq charge, the electric potential at the center dvc is what? K dq divided by r. Correct? Now I have to find the total potential at center C, that is the integration of dvc. It is what? K by r integration of what? Dq. Now we will add all dq, it will become q. So because here, see here, r is same for all charges, whatever on the perimeter. Okay. So it will be same because it is equal distance. So r is constant, k is already constant. Now we have to integrate dq. So dq, if you will integrate, if you will add, it is total charge. So it can be directly written as k q by r. So in this way, we can find at the center of the ring what is the electric potential due to uniformly charged ring. Correct? Now we will discuss at the axial point. For example, if I will take a uniformly charged rod, and here I will take the charge on it, let the total charge is q. Q is what? Total charge. And the radius of the ring is r. And at axial point I'm finding. This is what? At axial point. Correct? So here from the center, the distance I consider x of this point P. Now as I discussed, whenever extended body is there, you have to take the elemental charge. So let elemental charge dq is there. This elemental charge dq, what distance from point P? So this is r, radius is r. X is the distance from the center. So this will be root under r square plus x square, because this is forming right angle triangle. Now at point P, because scalar quantity, nothing, we should no need to think about the direction. Directly we can find, due to small charge, electric potential is what? dV k dq divided by distance is root under r square plus x square. Now we will integrate this to find net electric potential at point P. So here, first, x, r, and k all are constant. Normally, as I'm finding the students get confused. If it is x, they are thinking it is a variable. No, x doesn't mean variable. Here we have to check from center to point P. The distance is changing. No, distance is not changing. It is fixed. Point P we have to find. It means it is fixed point. So x is also fixed. If x is fixed, x is constant. So this whole term will become constant, root under r square plus x square. K is already constant. So constant will come outside, k divided by root under r square plus x square. Integration of what? dq. Now again, dq, if you will integrate, total charge will be q. Integration of dq is what? Total charge q. Okay. So here we will write k q divided by root under r square plus x square, where r is the radius of the ring. You can check this one by keeping at, for example, if this point P will come at center, that means if you have to find electric potential at center, what will happen? X becomes 0. X becomes 0. So at center, what happened? X becomes what? 0. If X becomes 0, then we'll put here 0. So it will become what? V at P. K q divided by root under r square plus 0 square. So finally it will come what? Kq by r. This is same like as a case 1. Correct now? So this formula is valid for all the point that is passing from the center of the ring along the axial line. Correct now? So in this lecture, we have studied about the basics of the electric potential. In the next lecture, we will relate electric field with the electric potential, and we will solve the problems based on these concepts. Thank you.